Well, welcome back to our course on system engineering. In this lecture, we're going to be talking about system development process. And just to give some context as a reminder, we have 5 sections that we'll be covering in our textbook. And so this is the third of 4 chapters in the foundations that are important for system engineering. And we're closely following along with our textbook, Systems Engineering Principles and Practice. And so I'd strongly recommend that you go ahead and take advantage of the material in the textbook, but also with what we're doing in the lecture notes. Hopefully this will be another way to give you some insight into what we're getting into. Okay, let's talk about systems engineering through the system lifecycle. As was described in a previous chapter and previous lecture as well, modern engineered systems come into being in response to societal needs or because of new opportunities offered by advancing technology, or both. The evolution of a particular new system from the time when a need for it is recognized and a feasible technical approach is identified through the development and introduction into operational use. It is a complex effort which will be referred to as a system development process. So in this chapter, in this lecture, it is devoted to describing the basic system development process and how system engineering is applied at each step of the process. You'll see that some of these diagrams will be referred to again as we go through the system life cycle. A typical major system development exhibits the following characteristics. It is a complex effort. It meets an important user need. It usually requires several years to complete. It is made up of many interrelated tasks. It involves several different disciplines. It is usually performed by several organizations. It has a specific schedule and budget. So those are the things to keep in consideration. The development and introduction into use of complex system inherently requires increasingly large commitments of resources as it progresses from concept through engineering, production, and operational use. Further, the introduction of new technology inevitably involves risk, which must be identified and resolved as early as possible. These factors require that the system development be conducted in a step-by-step manner in which the success of each step is demonstrated and the basis for the next one validated before a decision is made to proceed to the next step. So that's a little bit of an overview. One of the models that is quite common is the Department of Defense System Lifecycle Model. And so this would be a great way for us to give an understanding of the life cycle model. NASA also has a good one as well. The term system life cycle is commonly used to refer to the stepwise evolution of a new system from concept through development and on to production, operation, and ultimate disposal. As a type of work evolves from analysis to early conceptual phases to engineering, development, and testing to production and operational use, the roles of system engineering changes accordingly. As noted previously, the organization of this book and what we're following along these lectures is designed to follow the structure of the system life cycle so as to more clearly relate system engineering functions to the role in specific periods during the life of the system. This chapter and this lecture represents an overview of the system development process to create a context for the more detailed discussion of each step in the later chapters as well as later lectures. Development of a system engineering lifecycle model. Systems life cycle models have evolved significantly over the past several decades. Furthermore, the number of models has grown as additional unique and custom applications were explored. Additionally, software engineering has spawned a significant number of development models that have been adopted by the systems community. The end result is that there is no single life cycle model that one is accepted worldwide and two fits every possible situation. Various standard organizations, government and agencies and engineering communities have published their particular models or frameworks that can be used to construct a model. Therefore, adopting one model to serve as the appropriate framework for the book, as well as what we're going to cover in the lectures, may not be prudent. Fortunately, all life cycle models divide the system into a set of basic steps that separate major decision milestones. Therefore, the derivation of a life cycle model to serve as an appropriate framework for what's covered in the textbook and also these lectures had to meet two primary objectives. First, the steps in the life cycle had to correspond to the progressive transition in the principal system engineering activities. Secondly, the steps had to be capable of being mapped into the principal life cycle models in use by the system engineering community. The derived model will be referred to as the, quote, system engineering life cycle and will be based on three different sources. The Department of Defense Acquisition Management Model, also called DoD 5000.2, the International Model, ISO/IEC 1528, and the National Society of Professional Engineers, NSPE model. For the Department of Defense Acquisition Management model, the United States has been in the forefront of developing large-scale complex military systems such as warships, airplanes, tanks, and command and control systems. To manage the risk in the application of advanced technology and to minimize costly technical or management failures, the DoD has evolved comprehensive system acquisition guidelines, which are contained in DoD 5000 series of directives. The DoD lifecycle model, which reflects the acquisition guideline, is displayed in the figure that we're showing here. It consists of 5 phases: material solution analysis, technology development, engineering and manufacturing development, production and deployment, and operation and support. The 2 activities of user need determination and technology opportunity and resources are considered to be part of the process, but are not included in the formal portion of the acquisition cycle. The model is tailored towards managing large, complex system development efforts where reviews and decisions are needed at key events throughout the life cycle. The major reviews are referred to as milestones and are given letter designations A, B, and C. Each of these 3 major milestones is defined with respect to entry and exit conditions. For example, a milestone A, a requirement document needs to be approved by a military oversight program committee before a program will be allowed to transition to the next phase. In addition to milestones, the process contains 4 additional decision points: material development decision, MDD, preliminary design review, PDR, critical design review, CDR, and full rate production, FRP, decision review. Therefore, DoD management is able to review and decide on the future of the program at up to 7 major points within the life cycle. For the international ISO IEC 15288 model, the ISO/IEC issue a systems engineering standard designation, ISO/IEC 15288, system engineering, systems lifecycle process. The basic model is divided into 6 stages and 25 primary processes. The processes are intended to represent a menu of activities that may need to be accomplished within the basic stages. The ISO standard purposely does not align the stages and processes. The 6 basic stages are concept, development, production, utilization, support, and retirement. Then we have the professional engineering model, the NSPE. It is tailored to the development of commercial systems. The model is mainly directed to the development of new productions, usually resulting from technological advances, that is, technology drivers. Thus, the NSPE model provides a useful alternative view to the DoD model of how a typical system lifecycle may be divided into phases. The NSPE lifecycle is partitioned into 6 stages: conceptual, technical feasibility, development, commercial validation and production preparation, full-scale production, and production support. If you look at other agencies in the US government, I already mentioned NASA, it has a different process than what's laid out here. But like, as we've mentioned, since we've talked about 3, there are some similarities. The Department of Energy also has a distinctive acquisition process that's tailored for the things that it needs to be focusing on. Okay, well, let's look at how the system lifecycle model fits into areas that we see are major parts of our book and what we're covering in this course. In structuring a lifecycle model that corresponds to significant transitions in system engineering activities throughout the system active life, it is found most desirable to subdivide the life cycle into 3 broad stages and partition these into 8 distinct phases. The structure is shown in this figure, and it is discussed in the information we're going to be talking about next. The names of these subdivisions were chosen to reflect the primary activities occurring in each part of the process. Inevitably, some of these names are the same or similar to the names of the corresponding part of one or more of the existing life cycles. For life cycles, software life cycle models, the system life cycle stages and their constituent phases represented by the above model apply to the majority of complex systems, including those containing significant software functionality at the component level. However, software-intensive systems in which software performs virtually all of the functionality, as in modern financial systems, airline reservation systems, the World Wide Web, and other information systems, generally follow life cycles similar to Inform, but often involving iteration and prototyping. Another chapter that we'll get to later describes a difference between software and hardware. Discusses the activities involved in the principal stages of software system development and contains a section dealing with examples of software system lifecycle representing software-intensive systems. However, with that exception, the systems engineering lifecycle model, as will be discussed in other chapters, provides a natural framework for describing the evolution of the system engineering activities throughout the active life of engineered complex systems. Now, for systems engineering lifecycle stages, as we just discussed and illustrated in the figure, the systems lifecycle model consists of 3 stages. The first 2 encompassing the development part of the life cycle, and the third, the post-development period. These stages mark the more basic transitions in the system lifecycle, as well as changes in the type and scope of the efforts involved in the system engineering. In this book and the lectures that we're going to have, these stages will be referred to as 1, the conceptual stage, which is the initial stage of the formulation and definition of the system concept perceived to best satisfy a valid need. 2, the engineering development stage, which covers the transition of the system concept into a validated physical system design, meeting the operational cost and schedule requirements. And 3, the post-development stage, which includes the production, deployment, operation, and support of the system through its useful life. The names for the individual stages are intended to correspond generally to the principal types of activity characteristic of these stages. The concept development stage, as the name implies, embodies the analysis and planning that is necessary to establish the need for a new system, the feasibility of its realization, and the specific system architecture perceived to best satisfy the user needs. System engineering plays the lead role in transitioning to operational needs into technical and economically feasible system concept. There are some references in the textbooks like Mayer and Recton call the process system architecting, using the analogy of a building architect translating a client's need into plans and specifications that a builder can bid on and build from. The level of effort during this stage is generally much smaller than in the subsequent stages. The principal objective of the concept development stage are to, one, establish that there is a valid need and market for a new system that is technically and economically feasible. Two, explores system concepts and formulates and validate a set of system performance requirements. Three, select the most attractive system concept, define the functional characteristics, and develop a detailed plan for the subsequent stages of engineering, production, and operational deployment of the system. Four, develop any new technology called for the selected system concept and validate its capability to meet the requirements. Next, the engineering development stage corresponds to the process of engineering and the system to perform the functions specified in the system concept in a physical embodiment that can be produced economically and maintained and operated successfully in the operational environment. System engineering is the primary concern with guiding the engineering development and design, defining and managing interfaces, developing test plans, and determining how discrepancies in system performance uncovered during test and evaluation, sometimes called T&E, should best be rectified. The main bulk of the engineering effort is carried out during this stage. The primary objectives of the engineering development stage are: one, perform the engineering development of a prototype system satisfying the requirements of performance, reliability, maintainability, and safety. Engineer the system for economical production and use and demonstrate its operational suitability. And then the final phase, the post-development, the post-development stage consists of activities beyond system development period, but still require significant support from system engineering, especially when unanticipated problems requiring urgent resolution are encountered. Also, continuing advances in technology often require in-service system upgrading, which can be just as independent on system engineering, can be just as dependent on system engineering as the concept and engineering development stages. The post-development stage of a new system begins with the system successfully undergoing its operational T&E, test and evaluation, sometimes referred to the acceptance testing, and is released for production while subsequent operational use. While the basic development has been completed, system engineering continues to play an important role in this effort. Okay, now let's get into the principal stages in the system lifecycle. So the relationship among the principal stages in the system lifecycle are illustrated in the form of a flow chart, as we're showing here. The figure shows the principal inputs and outputs of each stage. The legends above the blocks relate to the flow of information in the form of requirements, specification, and documentations, beginning with the operational need. The input and outputs below the blocks represent the stepwise evolution of the design representations of an engineered system from concept to the operational system. It is seen that both the documentation and design representation become increasingly complete and specific as the life cycle progresses. Future sections, system materialization, is devoted to the discussion of the factors involved in this process. So we can be considering an example, the development stages of a new commercial aircraft. To illustrate the application of this life cycle model, consider the evolution of a new passenger aircraft. The concept development stage would include the recognition of a market for a new aircraft, the exploration of possible configurations such as number, size, and location of engines, body dimensions, wing platform, and so on, leading to the selection of the optimum configuration from the standpoint of production costs, overall efficiency, passenger comfort, and other operational objectives. The above decisions would be based largely on analyses, simulations, and functional designs, which collectively would constitute justification for selecting the chosen approach. The engineering development stage of the aircraft life cycle begins with the acceptance of the proposed system concept and a decision by the aircraft company to proceed with its engineering. The engineering effort would be directed to validating the use of an unproven technology, implementing the system functional design into hardware and software components, and demonstrating that the engineered system meets the user needs. This would involve building prototype components, integrating them into an operational system, and evaluating it in a realistic operational environment. The post-development stage includes the acquisition of production tooling and test equipment, production of the new aircraft, customizing it to fit requirements of different customers, supporting regular operations, fixing any faults discovered during use, and periodically overhauling or replacing engines, landing gear, and other highly stressed components. System engineering plays a limited but vital supporting and problem-solving role during this stage. Next, we'll walk through each of these stages in more detail, and these are exposing more of the things that we'll be covering in later chapters. So for the system life cycle, the concept development phases, while the three stages described above constitute the dominant subdivisions of the system life cycle, each of these stages contain recognizable subdivisions with characteristically different objectives and activities. In the case of large programs, formal decision points also mark most of these subdivisions, similar to those marking the transition between stages. Furthermore, the roles of system engineering tend to differ significantly among these intermediate subdivisions. Hence, to understand how the evolution of the system lifecycle relates to the system engineering process, it is useful to develop a model of a structure down to the second level of subdivision. Okay, so here is a diagram that shows those sub areas within the concept development phases, the concept development phase. So the concept development phase of the system engineering life cycle encompasses three phases: needs analysis, concept exploration, and concept definition. So this figure shows these phases, their principal activities and inputs and outputs in a format analogous to the figure that we just showed at the higher level. Now we're getting into more details. So let's talk about each of these. The needs analysis phase. The needs analysis phase defines that the need for a new system. It addresses the question, is there a valid need for a new system? And is there a practical approach to satisfying such a need? These questions require a crucial examination of the degree to which current perceived future needs cannot be satisfied by physical or operational modifications or available means, as well as whether or not available technology is likely to support the increased capability desired. In many cases, the beginning of the life of a new system evolves from continuing analysis of operational needs, or innovative product development without a sharply identified beginning. The output of this phase is a description of the capability and operational effectiveness needed in the new system. In many ways, this description is the first iteration of the system itself, albeit a very basic conceptual model of a system. The reader should take note of how the system evolves from the very beginning phase throughout its life cycle. Although we would not yet call this description a set of requirements, they certainly are the forerunner of what will be defined as the official requirements. The US DoD community refers to this early description as the initial capability description. Several classes of tools and practices exist to support the development of the system capabilities and effectiveness description. Most fall into two categories of mathematics known as operational analysis and operations research. However, technology assessments and experimentations are an integral part of this phase and will be used in conjunction with mathematical techniques. Next, we have the concept exploration phase. This phase examines potential system concepts and answering the question, what performance is required of the new system to meet the perceived need? And is there at least one feasible approach to achieve such performance at an affordable cost? Positive answers to these questions set a valid and achievable goal for a new system project prior to expending the majority of the effort in its development. The output of this phase includes our first, quote, official set of requirements, typically known as the system performance requirements, which we mean by official is that a contractor or agency can be measured against this set of requirement capabilities and performance. In addition to an initial set of requirements, this phase produces a set of candidate system concepts. Note the plural, more than one alternative is important to explore and understand the range of possibilities in satisfying the need. A variety of tools and techniques are available in this phase and range from process methods, that is requirements analysis, to mathematical based, that is decision-based support methods, to exploring judgment based on brainstorming oftentimes. Initially, the number of concepts can be quite large for some of these techniques. However, the set quickly reduces to a manageable set of alternatives, and it's important to understand and prove the feasibility of the final set of concepts that will become the input of the next phase. And thirdly, we have the concept development, concept definition phase. The concept definition phase selects the preferred concept and answers the question, what are the key characteristics of the system concept that would achieve the most beneficial balance between capability, operational life, and cost? To answer this question, a number of alternative concepts must be considered, and their relative performance, operational utility, development risk, and cost must be compared. Given a satisfactory answer to this question, a decision to commit major resources to the development of the new system can be made. The output is really two perspectives on the same system, a set of functional specifications that describe what the system must do and how well, and a selected system concept. The later can be in two forms. If the complexity of the system is rather low, a simple concept description is sufficient to communicate the overall design strategy for the development effort to come. However, if the complexity is high, a simple concept description is insufficient, and a more comprehensive system architecture is needed to communicate the various perspectives of the system. Regardless of the depth of the description, the concept needs to be described in several ways, primarily from a functional perspective and from a physical perspective. Further perspectives may very well be needed if complexity is particularly high. The tools and techniques available fall into two categories: analysis of alternatives and system architecting. As noticed previously in commercial projects, NSPE model, that is, the first two phases are often considered as a single pre-project effort. This is sometimes referred to as a feasibility study, and its result constitute a basis for making a decision as to whether or not to invest in a concept definition effort. In the defense acquisition lifecycle, the second and third phases are combined, but the part corresponding to the second phase is performed by the government, resulting in a set of system performance requirements, while that corresponding to the third can be conducted by a government contractor team or performed by several contractors competing to meet the above requirements. In any case, before reaching the engineering development stage, only a fractional investment has usually been made in the development of a particular system. Although some years and considerable effort may have been spent in developing a firm understanding of the operational environment and exploring relevant technology at the subsystem level. The ensuring stages are where the bulk of the investment will be required. Next, let's review the engineering development phases. And so we are continuing this process of thinking about how we're going to do this. And so the next slide will show a figure, but the engineering development phases has the activity, it will show the activities, inputs, and outputs of the constituent phases of the engineering development stage of the system lifecycle in the same format of what we've previously shown in the last two diagrams. And these are referred to as advanced development, engineering design, and integration and evaluation. So for the specifics here, and let's look at the diagram, and we'll go through these one at a time. For the advanced engineering, advanced development phase, the success of the engineering development stage of a system project is critically dependent on the soundness of the foundation laid during the concept development stage. So this just reiterates the fact that system engineering from the very start is very important. However, since the conceptual effort is largely analytical in nature and carried out with limited resources, significant unknowns invariably remain that are yet to be fully defined and resolved. It is essential that these unknown unknowns be exposed and addressed early in the engineering stage. In particular, every effort must be made to minimize the number as yet undisclosed problems prior to the transitioning the functional design and the associated system requirements into engineering specifications for the individual system hardware and software elements. The advanced development phase has two primary purposes. One, the identification and reduction of development risk, and two, the development of system design specifications. The advanced development phase is especially important when the system concept involves advanced technology not previously used in a similar application, or where the required performance stresses the system components beyond proven limits. It is devoted to designing and demonstrating the undeveloped parts of the system, to proving the practicality of meeting their requirements, and to laying the basis for converting the functional system requirements into system specifications and component design requirements. Systems engineering is central to the decision of what needs to be validated and how, and to the interpretation of these results. The phase corresponds to the defense acquisition phase called engineering and manufacturing development, once referred to as a demonstration and validation. When the risk of using unproven technology are large, this phase is often contracted separately, with contracts for the remaining engineering phase contingent on the success. Matching the purpose of this phase, the two primary inputs are the design specification and the validation development model. The specifications are a refinement and evolution of the earlier function specifications. The development model is the final outcome of a very comprehensive risk management task, where those unknowns mentioned above have been identified and resolved. That is what we mean when we use the adjective validated. The system engineer needs to be convinced that this system can be designed and manufactured before transitioning from the phase. Therefore, all risk at the phase must be rated as manageable before proceeding. Modern risk management tools and techniques are essential to reduce and ultimately mitigate risk inherent in the program. As these risks are managed, the level of definition continues to migrate down from the system to the subsystem. Furthermore, a set of specifications for the next level of decomposition at the component level occurs. In all of these cases, both experimental models and simulations are often employed at this stage to validate component and subsystem design concepts at minimum cost. Then we get into the engineering design phase. The detailed engineering design of the system is performed during this phase. Because of the scale of the effort, it is usually punctuated by formal design reviews. An important function of these reviews is to provide an opportunity for the customer or user to obtain an early view of the product, monitor its costs and schedule, and provide valuable feedback to the system developer. While the issues of reliability, producibility, maintainability, and other abilities have been considered in previous phases, they are of paramount importance in this engineering design phase. These type of issues are known as the specialty engineering, since the product consists of a set of component capable of being integrated and tested as a system. The system engineer is responsible for ensuring that the engineering design of the individual components faithfully implements the functional and compatibility requirements, and for managing the engineering change process to maintain interface and configuration control. The task of this phase deal with converting the component specifications into a set of component designs. Of course, testing these components is essential to occur immediately after design, or in some cases concurrently with design. One additional task is performed during these phases: the refinement of the system T&E plan, test and engineering plan. We use the term refinement to distinguish between the initial and continuation. The T&E plan is initially developed much earlier in the life cycle. At this phase, the T&E plan is largely finished, using the knowledge gained from the previous phases. The two primary outputs of the T&E plan are an engineered prototype. The prototype can take many forms and should not be thought of as the same as that we think of a software prototype. This phase may produce a prototype that is virtual, physical, or hybrid, depending on the program. For example, if the system is an ocean-going cargo vessel, the prototype at this stage may be a hybrid of virtual and physical mock-ups. A full-scale prototype of the cargo ship may not be possible or prudent at this phase. On the other hand, if the system is a washing machine, a full-scale prototype may be totally appropriate. Modern computer-aided design tools are available as design engineers perform their trade. System models and simulations are also updated as designs are finalized and tested. Next, we get into the integration evaluation phase. the process of integrating the engineered components of a complex system into a functioning whole and evaluating that the system's operation as a realistic environment is nominally part of the engineering design process because there is no formal break in the development program at this point. However, there is a basic difference between the role and responsibility of system engineering during the engineering design of the system elements and that during the integration and evaluation process. Since the textbook and what we're focused on in this lecture is focused on the functions of system engineering, the system integration and evaluation process is treated as a separate phase in the system lifecycle. It is important to realize that the first time a new system can be assembled and evaluated as an operating unit is after its components are fully engineered and built. It is at this stage that all the component interfaces must fit and component interactions must be compatible with the functional requirements. While there may have been prior tests at the subsystem level or at the level of a development prototype, the integrity of the total design cannot be validated prior to this point. It should also be noted that the system integration and evaluation process often requires the design and construction of complex facilities to closely simulate operational stimuli and constraints and measure the system's response. Some of these facilities may adapt from developmental equipment, but the magnitude of the task should not be underestimated. The outputs of this phase are twofold: the specification to guide the manufacturing of the system, typically called the system production specification, and is sometimes referred to as a production baseline, and the production system itself. The later includes everything necessary to manufacture and assemble the system and may include a prototype system. Modern integration techniques and T&E tools, methods, facilities, and principles are available to assist or enable the engineers in these tasks. Of course, before full-scale production can occur, the final production system needs to be verified and validated through an evaluation within the operational environment or a sufficient surrogate for the operational environment. Moving on, third and finally, we get into the post-development. And so this is the next thing. And so I'll focus on the figure here to walk through those details. So in the post-development phases, we first of all have the production phase, the production and deployment. And so the production phase is the first of the two phases comprising the post-development stage, which are exactly parallel to the defense acquisition phases of production and deployment and operations and support. No matter how effectively the system design has been engineered for production, problems inevitably arise during the production process. There are always unexpected disruptions beyond the control of project management. For example, a strike at a vendor plant, unanticipated tooling difficulties, bugs in critical software programs, or an unexpected failure in a factory integration test. Such situations threaten costly disruptions in the production schedule that require prompt and decisive remedial action. System engineers are often the only person qualified to diagnose the source of the problem and find an effective solution. Often a system engineer can devise a workaround that solves the problem for a minimal cost. This means that an experienced cadre of system engineers intimately familiar with the system design and operation needs to be available to support the production effort. Where specially engineering a system may be required, the system engineers are often best qualified to decide who should be called and when. Next, we have the operation and support phase. In the operation and support phase, there is even more critical needs for system engineering support. The system operations and maintenance personnel are likely to be only partially trained in the finer details of system operation and upkeep. While specially trained field engineers generally provide support, they must be able to call on experienced system engineers in case they encounter problems beyond their own experience. Proper planning for an operational phase includes provision of a logistic support system and training programs for operators and maintenance personnel. This planning should have major participation from systems and engineering. There are always unanticipated problems that arise after the system becomes operational that must be recognized and included in the logistics and training systems. Very often, the instrumentation required for training and maintenance is itself a major component of the system to be delivered. More complex systems have lifetimes of many years, during which they undergo a number of minor and major upgrades. These upgrades are driven by evolution in the system mission, as well as by advances in technology that offer opportunities to improve operation, reliability, or economy. Computer-based systems are especially subject to periodic upgrades whose cumulative magnitude may well exceed the initial system development. While the magnitude of an individual system upgrade is a fraction of that required to develop a new system, it usually entails a great many complex decisions requiring the application of systems engineering. Such an enterprise can be extremely complex, especially in the conceptual stage of an upgrade effort. Anyone that has undergone a significant home alteration, such as an addition of a one bedroom and bath, will appreciate the unexpected difficulty of deciding just how this can be accomplished in such a way as to retain the character of the original structure and yet realize the full benefits of the added portion, as well as to be performed by an affordable price. So that's a quick synopsis of that. Let's now move on to be exploring the evolutionary characteristics of the development process. The nature of system development process can be better understood by considering certain characteristics that evolve during the life cycle. 4 of these are described in the following sections. So the section, the predecessor system, discusses the contributions of the existing system on the development of a new system that is replacing it. The section system materialization describes a model of how a system evolves from a concept to an engineered product. The section, the participants, describes the composition of the system development team and how it changes during the life cycle. The section system requirements and specification describes how the definition of the system evolves in terms of system requirements and specifications as the development progresses. Okay, let's now talk about those. First, the predecessor system. The process of engineering a new system may be described without regards to its resemblance to current systems, systems meeting the same or similar needs. The entire concept and all of its elements are often represented as starting with a blank slate, a situation that is virtually never encountered in practice. In the majority of cases, when new technology is used to achieve radical changes in such operating as transportation, banking, or armed combat, there exist predecessor systems. In a new system, the changes are typically confined to a few subsystems. While the existing overall system architecture and other systems remains substantially unchanged. Even the introduction of automation usually changes the mechanics, but the substance of the process. Thus, with the exception of such breakthroughs as the first generation of nuclear systems or of a spacecraft, a new system development can expect to have a predecessor system that can serve as a point of departure. A predecessor system will impact development of a new system in three ways. First, the deficiency of the predecessor system are usually recognized, often being the driving force for a new development. This focuses attention on the most important performance capabilities and features that must be provided by the new system. Two, if the deficiencies are not so serious as to make the current system worthless, its overall concept and functional architecture may constitute the best starting point for exploring alternatives. Three, to the extent that substantial portions of the current system perform their function satisfactorily and are not rendered obsolete by recent technology, great cost savings and risk reduction may be achieved by utilizing them with minimal changes. Given the above, the average system development will almost always be a hybrid, in that it will combine new and undemonstrated components and subsystems with previous engineered ones and fully proven ones. It is a particular responsibility of system engineering to ensure that the decisions as to which predecessor elements to use, which to reconsider, which to replace by new ones, and how these are to be interfaced are made through careful weighing of performance, cost, schedule, and other essential criteria. Okay, well, continuing our conversation, let's be thinking about the evolution of systems and life cycle, and let's focus on system materialization. The steps in the development of a new system can be thought of as an orderly, progressive materialization of the system from an abstract need to an assemblage of actual components, cooperating to perform a set of complex functions to fulfill that need. To illustrate this process, we can see in this table that it traces the growth of the materialization throughout the phases of the project lifecycle. And you can see how things get more complicated. There's more details as we progress in the stages. The rows of the table represent the levels of a system subdivision, from the system itself at the top to the part level at the bottom. The columns are successive phases of the system lifecycle. The entries are the primary activities at each system level and phase, and their degree of materialization. The shaded areas indicate the focus of the principal efforts in each phase. It is seen that each successive phase defines, that is, materializes the next lower level of system subdivision until every part has been fully defined. Examining each row from left to right, say at the component level, it is also seen that the process of definition starts with visualization, that is selecting the general type of system elements, then proceeds to defining its functions, that is functional design, what it must do, and then its implementation that focuses on detailed design of how it will do it. This above progression holds true through the engineering design phase, when the components of the system are fully materialized as finished system building blocks. In the integration and evaluation phase, the materialization process takes place in a distinctly different way, namely in terms of materialization of an integrated and validated operational system from its individual building blocks. It is important to note from the table that that while the detailed design of the system is not completed until near the end of the development, its general characteristics must be visualized early in the process. This can be understood from the fact that the selection of the specific system concept requires a realistic estimate of the cost to develop and produce it, which in turn requires a visualization of the general physical implementation as well as the functionality. In fact, it is essential to have at least a general vision of the physical embodiment of the system functions during even the earliest investigation of technical feasibility. It is, of course, true that these early visualizations of the system will differ in many respects from its final materialization, but not so far as to invalidate conclusions about its practicality. The role of system architecting fulfills the visualization requirement by providing visual perspectives into the system concept early in the life cycle. As the system project progresses through its life cycle, the products of the architecture are decomposed to even lower levels. At any point in the cycle, the current stage of the system definition can be thought of as the current system model. Thus, during the concept development stage, the system model includes only the system functional model that is made up entirely of descriptive material, diagrams, tables of parameters, and so on, in combination with any simulations that are used to examine the relationship between system level performance and specific features and capabilities of the individual system elements. Then during the engineering development stage, the model is augmented by the gradual addition of hardware and software designs for the individual subsystems and components, leading finally to the completed engineering model. The model is then further extended to a production model as an engineered design is transferred into producible hardware designs, detailed software definition, production tooling, and so on. At every stage of the process, the current system model necessarily includes models of all externally imposed interfaces as well as internal system interfaces. Next, let's talk about the evolution of system representation. So in terms of system requirements and specification, just as the system design gradually materializes during the successive steps of system development, so the successive forms of system requirements and specifications become more and more specific and detailed. These start with a set of operational requirements and end with a complete set of production specifications, operation, maintenance, and training manuals, and all other information needed to replicate, operate, maintain, and repair the system. Thus, each phase can be thought of as producing a more detailed description of the system, what it does, how it works, and how it is built. Since the above document collectively determine both the course of the development effort and the form and capability of the system as finally developed, oversight of the definition and preparation is a primary responsibility of system engineering. This effort must, however, be closely coordinated with the associated design specialists and other involved organizations. The evolution of the system requirements and specification is shown in the second row of what we're listing here in this table as a function of the phases in the system lifecycle. It should be emphasized that each successive set of documents does not replace the version defined during the previous phase, but rather supplements it. This produces an accumulation rather than a succession of system requirements and other documents. These are, quote, living documents which are periodically revised and updated. The necessity for an aggregation of formal requirements and specifications developed during successive phases of the system development can be better understood by recalling the discussion of participants and in an earlier figure, which was that we talked about. In participants, not only are many different groups engaged in the development process, but many, if not most, of the key participants change from one phase to the next. This makes it essential that a complete and up-to-date description exists that defines what the system must do, and also, to the extent previously defined, how it must do it. The system description document not only lays out the basis for the next phase of system design, but they also specify how the results of the effort are to be tested in order to validate compliance and the requirements. They provide the information base needed for devising both the production tools and the tools to be used for inspection and testing the product of the forthcoming phase. The representation of system characteristics are also evolved during the development process. As indicated in the second row of the table, most of these will be recognized as architecture views and conventional engineering design and software diagrams and models. The purpose is to supplement textual descriptions of successive stages of system materialization by more readily understandable visual forms. This is especially important in defining interfaces and interactions among system elements designed by different organizations. So just as a reminder, just going back to one slide, this is the principal participation in system development as we go from one phase to another. And so I was mentioning that. So you can either pause there or we talked about this chart already. But moving forward, let's talk about the system engineering method. So in the preceding sections, the engineering of a complex system was seen as divisible into a series of steps or phases, beginning with the identification of the opportunity to achieve a major extension of an important operational capability by a feasible technological approach. Each succeeding phase adds a further level of detailed definition, that is materialization of the system, until a fully engineered model is achieved that proves to meet all essential operational requirements reliably and at an affordable cost. While many of the problems addressed in a given phase are peculiar to that state of the system definition, the system engineering principles that are employed and the relation among them are fundamentally similar from one similar from one phase to the next. This fact and its importance is understanding that the system development process has been generally recognized. The set of activities that tends to be repeated from one phase to the next have been referred to in various publications on system engineering as the, quote, system engineering process or system engineering approach. And it is the subject of the next section here and what we'll be covering in this lecture. We can also be thinking about it as the system engineering method. And in this iterative set of activities will be referred to as the system engineering method. And so, like I just stated, so let's go ahead and get into the details. The reason for selecting the word method is to place of the more widely used process or approach is that it provides more definitive and less ambiguous phraseology. The word method is more specific than process, having the connotation of orderly and logical terms. Furthermore, the term system engineering process is sometimes used to apply to the total system development. Method is also more appropriate than approach, which connotates an attitude rather than a process. With all that said, the use of the more common terminology is perfectly acceptable. So let's get into the system engineering method. The system engineering method can be thought of as a systematic application of the scientific method to the engineering of complex systems. It can be considered as consisting of 4 basic activities applied successfully as illustrated in the figure that we'll get into next. So a high level and then a more detailed view. So the requirements analysis is first, the functional definition, the physical definition, and the design validation. These steps will vary in their specifics depending on the type of system and on the phase of the development. However, there is enough similarity in these operational principles that it is useful to describe the typical activities of each step in the method. Such brief descriptions of the activities in these four steps are discussed next, and so let's just go through them. So first of all, the requirements analysis. This is the problem definition, and it's the typical activities include assessing the organization of all input conditions, including requirements, plans, milestones, and models from the previous phase. Identifying the whys of all requirements in terms of operational needs, constraints, environments, or other high-level objectives. Clarifying the requirements of what the system must do, how well it must do it, and what constraints it must fit. And finally, correcting inadequacies and quantifying the requirements whenever possible. For the functional definition, which is dealing with functional analysis and allocation, the typical activities include translating requirements, that is why, into function, that is actions and tasks, that the system must accomplish, which is focusing on what. Next, partitioning is the allocating process of requirements into functional building blocks. Next, defining interactions among functional elements to lay a basis for their organization into a modular configuration. Then we have the physical definition, which is a synthesis, physical analysis and allocation. The typical activities include synthesizing a number of alternative systems, components representing a variety of design approaches to implementing the required functions, and having the most simple, practical interactions and interfaces among structural subdivisions. Then there's selecting a preferred approach by trade-offs, a set of predefined and prioritized criteria. Gets into measures of effectiveness, or MOEs, to obtain the best balance among performance, risk, cost, and schedule. Finally, we have elaborating the design to the necessary level of detail. For design validation, it's dealing with verification evaluation. The typical activities include design models of the system environment, logical, mathematical, simulated, and physical, reflecting all significant aspects of the requirements and constraints. Simulation or testing of testing and analyzing system solutions against environmental models. And finally, iterating as necessary to revise a system model or environmental models, or to revise system requirements if too stringent for a viable solution, until the design and requirements are fully compatible. Okay, so we can see this general process, the system engineering top-level methods flow. The elements of the system engineering method are described above, are displayed in the form of a flow diagram here, and then we'll have an expanded view over 4 pages next. The rectangular blocks are seen to represent the above 4 basic steps in the method: requirements analysis, functional definition, physical definition, and design validation. At the top are shown inputs from the previous phase, which includes requirements, constraints, and objectives. At the left of each block are shown the external inputs, such as the predecessor system, system building blocks, and previous analysis. At the upper right of the top blocks and at the very bottom are inputs from system engineering methodology. And so here we have this broken up into 4 slides here, and we'll talk about this. The circles inside each blocks are simplified representations of key processes in that step of the method. The interfacing arrows represents information flow. If it is seen that there are feedbacks throughout the process, iterations from the elements as well as prior elements, and indeed all the way back to the requirements. Each of these elements of the method is described more fully in the remainder of the section, so we'll just get at it one at a time. So let's look at the requirements analysis, which is the problem definition. In attempting to solve any problems, it is first necessary to understand exactly what is given, and to the extent that it appears to be incomplete, inconsistent, or unrealistic, to make appropriate applications or corrections. This is particularly essential in the system development process, where a basic characteristic of system engineering is that everything is not necessarily what it seems, and that important assumptions must be verified before they are accepted as being valid. Thus, in a system development project, it is the responsibility of system engineering to thoroughly analyze all requirements and specifications, first in order to understand the vis-a-vis the basic needs that the system is intended to satisfy, and then to identify and correct any ambiguities or inconsistencies in the definition of the capabilities for the system or system elements being addressed. The specific activities of the requirements analysis vary as a system development progresses, as the inputs from the previous phase evolve from operational needs as technological opportunities, where we can be exploring this in the figure, to increasingly specific representations of requirements and system design. The role of system engineering is essentially throughout, but perhaps more so in the early phases, where an understanding of the operational environment and the availability and maturity of applicable technologies are most critical. In later phases, environmental interface and other inner element requirements are this special province of system engineering. For organization interpretation in a well-structured acquisition process, a new phase of the system lifecycle begins with three main inputs, which are defined during or upon completion of the previous phase. The system design model, which identifies and describes all design choices made and validated in the preceding phases, requirements or specifications that define the design, performance, and interface compatibility features of the system or system elements to be developed during the next phase. These requirements are derived from previously developed higher level requirements, including any refinement and or revisions introduced during the latest phase. Three's specific progress to be achieved by each component of the engineering organization during the next phase, including the identification of all technical design data, hardware/software products, and associated test data to be provided. The information is usually presented in the form of a series of independent task statements. Then there's a clarification, correction, and qualification. It is always difficult to express objectives in unambiguous and qualitative terms, so it is therefore common that stated requirements are often incomplete, inconsistent, and vague. This is especially true if the requirements are prepared by those who are unfamiliar with the process of converting them to system capabilities, or with the origin of the requirements in terms of operational need. In practice, the completeness and accuracy of these inputs can be expected to vary with the nature of the system, its degree of departure from predecessor systems, and the type of acquisition process employed, and the phase itself. The above analysis must include interactions with the prospective users of the system to gain a firsthand understanding of their needs and constraints, and to obtain their inputs where appropriate. The result of the analysis may be modifications and amplifications of the requirement document so as to better represent the objectives of the program or the availability of the proposed technological improvements. The end objective is to create a firm basis from which the nature and location of the design changes needed to needed to meet the requirements may be defined. So now we get into the next stage, the functional definition, the functional analysis and allocation. In the systems engineering method, functional design precedes physical or production design to ensure a disciplined approach to an effective organization, that is, configuration of the functions, and to the selection of the implementation that best balances the design characteristics of the system, that is, the performance and cost. Then, considering transition into functions as system elements that may serve as functional building blocks are briefly discussed in another chapter. The building blocks are at the component level, representing elements that perform a single significant function and deal with a single medium that is either signals, data, material, or energy. Then in turn consist of sub-elements performing lower level functions and aggregate into functional subsystems. Thus, functional subsystems, thus functional design can be thought of as selecting, subdividing, or aggregating functional elements appropriate to the required task and level of a system materialization. The decomposition and allocation of each iterative set of requirements and functions for implementation at the next lower level of system definition is a prime responsibility of system engineering. This first takes place during the concept development stage as follow-up to the definition of the system architecture. It includes identification and description of all functions to be provided, along with the associated quantitative requirement to be met by each subsystem in order that the prescribed system level capabilities can be, in fact, be achieved. This information is then reflected in system functional specifications, which serve as the basis for follow-on engineering in the development stage. As a part of the advanced development phase, these top-level subsystem functions and requirements are further allocated to individual system components within each subsystem. This, as noted earlier, is the lowest level in the design hierarchy that is of direct concern to system engineering, except in special cases where lower-level elements turn out to be critical to the operation of the system. Then there's trade-off analysis, the selection of appropriate functional elements. As all aspects of design is an inductive process in which a set of postulated alternatives are examined and the one judged to be best for the intended purpose is selected. The system engineering method relies on making design decisions by the use of trade-off analysis. Trade-off analysis is widely used in all types of decision-making, but in systems engineering, it is applied in a particular discipline form, especially in the step of physical definition. As the name implies, trade-offs involve the comparison of alternatives, which are superior to one or more required characteristics, with those that are superior to in others to ensure that an especially desirable approach is not overlooked. It is necessary to explore a sufficient number of alternative implementations, all defined to a level adequate to enable their characteristics to be evaluated relative to one another. It is also necessary that the evaluation be made relative to a carefully formulated set of criteria, measures of effectiveness, or MOE. Note that the model-based system engineering, MBSE, is particularly well suited to support various levels of automated trade study because relevant information about the system of interest is contained in a model that can exchange information directly from various simulation and analysis tools. Then we have functional interactions. One of the single most important steps in system design is the definition of the functional and physical interactions and interfaces interfacing of the building blocks. A necessary ingredient in this activity is the early identification of the significant functional interactions and the way in which the functional elements may be aggregated so as to group strongly interacting elements together and make the interactions among the groups as simple as possible. Such organization, that is, architectures, are reflected to be modular and are the key to system design that are readily maintainable and capable of being upgraded to extend their useful life. Another essential ingredient is the identification of the external interactions and the interfaces through which they affect the system. Next, we get into the physical definition, dealing with synthesis or physical analysis and allocation. This physical definition is a transition of the functional design into hardware and software components and the integration of these components into the total system. In the concept development stage, where all design is still at the functional level, it is nevertheless necessary to visualize or imagine what the physical embodiment of the concept would be like in order to help ensure that the solution will be practically realizable. The process of selecting the embodiment to be visualized is also governed by the general principle discussed below, applied more qualitatively than the engineering development than in the engineering development stage. So first, let's think about the synthesis of alternative system elements. The implementation of functional design elements requires decisions regarding the specific physical form that the implementation should take. Such decisions include choice of implementation media, element form, arrangement, and interface design. In many instances, they also offer a choice of approaches, range from exploiting the latest technology to relying on proven techniques. As in the case of functional design, such decisions are made by the use of trade-off analysis. There usually being more choices of different physical implementation than functional configurations. It is even more important that good system engineering practice be used in the physical definition process. Next, selection of the preferred approach. At various milestones in the system lifecycle, selecting of a preferred approach or approaches will need to be made. It is important to understand that the selection processes changes depending on the phase within the life cycle. Early phases may require selecting several approaches to explore, while later phases may require a down select to a single approach. Additionally, the level of decisions evolve. Early decisions relate to the system as a whole. Later decisions focus on subsystems and components. As stated previously, to make a meaningful choice among design alternatives, it is necessary to define a set of evaluation criteria and establish their relative priority. Among the most important variables to be considered in the physical definition step is the relative affordability or cost of the alternatives and their relative risk of successful accomplishment. In particular, early focus on one particular element concept should be avoided. Risk as a component of trade-off analysis is basically an estimate of the probability that a given design approach will fail to produce a successful result, whether because of deficient performance, lower reliability, excessive cost, or unacceptable schedule. If the component risk appears substantial, the risk to the overall project must be reduced, that is, risk abatement, by either initiating an intensive components development effort by providing a backup using a proven but somewhat less capable component, by modifying the overall technical approach to eliminate the need for a particular component that is in doubt, or if these fail, by relaxing the related system performance specification. Identifying significant risk item, high-risk system elements, and determining how to deal with them is an essential system engineering responsibility. We'll talk about this again in a later chapter that discuss the risk management process and its constituent parts. Proper use of the system engineering method thus ensure that 1, all viable alternatives are considered, 2, a set of evaluation criteria is established, and 3, the criteria are prioritized and quantified where practical. Whether or not it is possible to make a quantitative comparison, the final decision should be tempered by judgment based on experience. Okay, then finally, dealing with interface definition, implicit to the physical definition step is the definition and control of interfaces, both internal and external. Each element added or elaborated in the design process must be properly connected to its neighboring elements and to any external inputs or outputs. Further, as the next lower design level is defined, adjustments to the parent element will inevitably be required, which must be in turn be reflected in adjustments to their previously defined interfaces. All such definitions and readjustments must be incorporated into the model design and interface specifications to form a sound basis for the next level of design. Okay, well, finishing up with this 4-chart series, let's think about the design validation that is dealing with verification and evaluation. So in the development of a complex system, even through the preceding steps of the design definition may have been carried out apparently in full compliance with requirements, there still needs to be an explicit validation of the system before the next phase is undertaken. Experience has shown that there are just too many opportunities for undetected errors to creep in. The form of such validation varies with the phase and degree of the system materialization, but the general approaches is similar from phase to phase. So first of all, modeling the system environment. To validate a model of a system, it is necessary to create a model of the environment with which the system can interact to see if it produces the required performance. This task of modeling the system environment extends throughout the system development cycle. In the concept development stage, the model is largely functional, although some parts of it may be physical, as when an experimental version of a critical system component is tested over a range of ambient conditions. In later stages of development, various aspects of the environment may be reproduced in the laboratory or in a test facility, such as the aerodynamics, wind tunnel, or inertial test platform. In cases where the model is dynamic, it is more properly called a simulation, in which the system design is subject to time-varying inputs to stimulate its dynamic response modes. As the development progresses into the engineering development stage, modeling the environment becomes increasingly realistic, and environmental conditions are embodied in system and component test equipment, such as environmental chambers or shock and vibration facilities. During operational evaluation tests, the environment is, insofar as practical, made identical to that which the system will eventually operate. Here, the model has transitioned into greater reality. Some environments that are of greater significance to the system performance and reliability can only be imperfectly understood and are very difficult to stimulate. For example, the deep oceans and exoatmospheric space. In such cases, defining and simulating the environment may become a major effort in itself. Even environments that were thought to be relatively well understood can yield surprises. At each step, the system development process requires a successfully more detailed definition of the requirements that the system must meet. It is against these environmental requirements that the successive models of the system are evaluated and refined. A lesson to be learned is that the effort required to model the environment of a system for the purpose of system test and evaluation, T&E, needs to be considered at the same level of priority as the design of the system itself, and may even require a separate design effort comparable with the associated system design activity. For test and test data analysis, the definitive steps in the validation of the system design and the conduct of test in which the system model or a significant portion of it is made to interact with a model of its environment in such a way that the effects can be measured and analyzed in terms of the system requirements. The scope of such test evolves with the degree of the materialization of the system, beginning with paper calculations and ending with operational test in the final stages. In each case, the objective is to determine whether or not the results conform to those prescribed by the requirements, and if not, what changes are required to rectify the situation. In carrying out the above process, it is most important to observe the following key principles. 1, all critical system characteristics need to be stressed beyond their specified limit to uncover incipient weak spots. 2, all key elements need to be instrumented to permit location of the exact sources of deviation in behavior. The instrument must be significantly exceed the test article in precision and reliability. 3, a test plan and an associated test data analysis plan must be prepared to assure that the requisite data are properly collected and are then analyzed as necessary to assure a realistic assessment of system compliance. 4, all limitations in the test due to unavoidable artificialities need to be explicitly recognized in their effect on the result, compensated or corrected for as far as possible. 5, a formal test report must be prepared to document the degree of compliance by the system and the source of deficiencies. The test plan should detail each step in the test procedure and identify exactly what information will be recorded prior to, during, and at the conclusion of each test step, as well as how and by whom it will be recorded. The test data analysis plan should then define how the test would be reduced, analyzed, and reported, along with specific criteria that will be employed to demonstrate system compliance. To the extent that the validation test reveal deviations from required performance, the following alternatives can be considered. 1, can the deviation be due to a deficiency in the environmental simulation, say the test equipment? This can happen because of the difficulty of constructing a realistic model of the environment. 2, is a deviation due to a deficiency in the design? If so, can it be remediated without extensive modification to other system elements? 3, is the requirement at issue overall overly stringent? If so, a request for a deviation may be considered. This would constitute a type of feedback that is characteristic of the system development process. In terms of preparation for the next phase, each phase in the system development process produces a further level of requirements or specification to serve as a basis for the next phase. This adds to rather than replaces previous levels of requirements and serves two purposes. One, it documents the design decisions made in the course of the current phase. Two, it establishes the goal for the succeeding phase. Concurrent with the requirements analysis and allocation activities, system engineering, acting in concert with project management, is also responsible for the definition of specific technical objectives to be met and for the production, that is hardware and software components, technical documentation, supporting test data that will be provided in response to the stated requirements for input to the next phase. These identified end products of each phase are also often accompanied by a set of intermediate technical milestones that can be used to judge technical progress during each particular design activity. The task of defining these requirements or specifications and the effort to be undertaken in implementing the related design activities is an essential part of the system development. Together, these constitute the official guide for the execution of each phase of the development. It must, however, be noted that in practice, the realism and effectiveness of the effort, which is so critical to the ultimate success of the project, depends in large part on good communication and cooperation between system engineering and project management on the one hand, and on the other hand, the design specialists who are ultimately the best judge of what can and cannot be reasonably accomplished given the stated requirements, availability, available resources, and allocated timescale. Since the nature of the preparation for the next phase varies wildly from phase to phase, it is not usually accorded the status of a separate step in the system engineering method. Most often it is combined with the validation process. However, this does not diminish its importance because the thoroughness with which it is done directly affects the requirements analysis process at the initiation of the next phase. In any event, the definition of the requirements and stages to be performed in the next phase serves as an important interface function between phases. Next, let's talk about the spiral model of system lifecycle. The spiral lifecycle model, the iterative nature of system development process with a successive application of the system engineering method to a stepwise materialization of the system, has been captured in the so-called spiral model of the system lifecycle. A version of this model as applied to the lifecycle phases is shown here in the figure. So you start here and you gradually start to get closer and closer to the center. The sectors represent the 4 steps in the system engineering method definition in the previous sections and are shown separately by heavily radial lines. The model emphasizes that each phase of the development of a complex system necessarily involves an iterative application of the system engineering method and the continuing review and updating of the work performed and conclusions reached in the prior phases of efforts. Okay, let's now think of about the testing throughput system development. And so testing and evaluations are not separate functions from design, but rather inherent parts of design. In basic types of designs, for example, as a picture, the function of test and evaluation, T&E, is performed by the artist as part of the process of transforming a design concept to canvas. To the extent that the painting does not conform to the artist's intent, he or she alters the picture by adding a few brushstrokes, which tailor the visual effect, that is the performance, to match the original objective. Thus, design is a closed-loop process in which test and evaluation, T&E, constitutes the feedback that adjusts the results to the requirements that is intended to meet. So let's talk about a couple of things, unknowns. And so in any new system development project, there are a great many unknowns that need to be resolved in the course of producing a successful product. For each significant departure from established practices, the result cannot be predicted with assurance. The project cost depends on a host of factors, none of them known precisely. The resolution of interface incompatibilities are often involves design adjustments on both sides of the interface, which frequently leads to unexpected and sometimes major technical difficulties. An essential task of system engineering is to guide the development of the system so that the unknowns are turned into knowns as early in the process as possible. After surprises occurring later in the process can prove to be many times more costly than those encountered in the early phases. Many unknowns are evident at the beginning and may be called known unknowns. These are identified early as potential problem areas and are therefore singled out for examination and resolution. Usually they can be accomplished through a series of critical experiments involving simulation and/or experimental hardware and software. However, many other problems areas are only identified later when they are discovered during system development. These unanticipated problems are often identified as unknown unknowns, and so there is a distinction between known unknowns and unknown unknowns. And let's think about the transforming the unknowns into knowns. The existence of the unknown unknowns makes the task of attempting to remove all of the unknowns far more difficult. It forces an active search for hidden traps in the favored places of technical problems. It is the task of the system engineer to lead this search based on experience gathered during previous system development and supported by a high degree of technical insight and a what-if attitude. Since every unknown poses an uncertainty in the accomplishment of the final objective, it represents a potential risk. In fact, unknowns present the principal risk in any development program. Hence, the task of risk assessment and an integration is one and the same as that of identifying unknowns and resolving them. The tools for resolving unknowns are analysis, simulation, and test, these being the means for discovering and quantifying critical system characteristics. The effort begins during the earliest conceptual stages and continues throughout the entire development, only changing in substance and character and not in objective and approach. In designing a new system or a new element of a system that requires an approach never attempted before under the same circumstances, as for example, the use of a new materials for making a highly stressed design element, the designer faces a number of unknowns regarding the exact manner in which the new design, when implemented, will perform. For example, the elements made of a new material may not be capable of being formed into the required shape by conventional tools. In such cases, the process of testing serves to reveal whether or not the unknown factors create unaccepted difficulties requiring significant design changes or even abandonment of the approach. When a new design approach is undertaken, it is unwise to wait until the design is fully implemented before determining whether or not the approach is sound. Instead, testing should first be done on a theoretical or experimental model of the design element, which can be created quickly and at minimum cost. In doing so, a judgment must be made as to the balance between the potential benefit of a greater degree of realism of the model and the time and cost of achieving it. This is very often a system level rather than a component level decision, especially if the performance of the element can have a system impact. If the unknowns are largely in the functional behavior of the element, then a computational model or a simulation is indicated. If, on the other hand, the unknowns are concerned with the material aspects, an experimental model is required. Next, system engineering approach to testing. The system engineering approach to testing can be illustrated by comparing the respective views of the testing by the design engineer, the test engineer, and the system engineer. The design engineer wants to be sure that the component passes the test, wanting to know, is it okay? The test engineer wants to know that the test is thorough as to be sure that the component is stressed enough. The system engineer wants to be sure to find and identify all deficiencies present in the component. If the component fails a test, the system engineer wants to know why, so that there will be a basis for devising changes that will eliminate the deficiency. It is evident from the above that the emphasis of system engineering is not only on the test conditions, but also on the acquisition of the data, showing exactly how the various parts of the system did or did not perform. Furthermore, the acquisition of data itself is not enough. It is necessary to have in hand procedure for analyzing the data. These are often complicated and require sophisticated analytical techniques, which must be planned in advance. It also follows that a system engineer must be an active participant in the formation of the test procedure and choices of instrumentation. In fact, the primary initiative for developing the test plan should lie with system engineering, working in close cooperation with test engineering. To the system engineer, a test is like an experiment is to a scientist, namely a means of acquiring critical data on the behavior of the system under controlled circumstances. And then finally, system T&E, test and evaluation. The most intensive use of testing in the system lifecycle takes place at the last phase of the system development, integration, and evaluation, which is the subject of another chapter. Another chapter also contains a section on test and evaluation during the advanced development phases. So that's a nice overview of the different things that we've covered in this chapter. Okay, finally, let's review the things that we've covered in this chapter and in this lecture. We'll be thinking about system engineering throughout the life cycle. Number one, major system development program is an extended complex effort to satisfy an important user need. It involves multiple disciplines and applies new technology requirements, progressively increasing commitment of resources, and is conducted in a stepwise manner to a specified schedule and budget. For system lifecycle, the system lifecycle may be defined into three major stages: the concept development. The system engineering establishes the system need, explores feasible concepts, and selects a preferred system concept. The concept development stage may be further subdivided into three phases: the needs analysis. It defines and validates the need for a new system, demonstrates its feasibility, and defines system operational requirements. 2, the concept exploration explores feasible concept and defines functional performance requirements. And 3, concept definition examines alternative concepts, selects preferred concepts on the basis of performance, cost, schedule, and risk, and defines a system functional specification, sometimes called an A-spec. Then there's the engineering development. The system engineering validates new technology, transforms the selected concepts into hardware and software design, and builds and tests production models. The engineering development stage may be further subdivided into 3 phases. 1, advanced development identifies areas of risk, reduces these risks through analysis, development, and test, and defines system development specifications, which is sometimes called a B-spec. 2, engineering design performs preliminary and final design and builds and tests hardware and software components, or CIs. And 3, integration and evaluation integrates components into production prototypes, evaluates prototypes, systems, and rectifies deviations. Then there's post-development. System engineers produce and deploy the system and support system operations and maintains the post-development stage into its further subdivided into 2 phases. Production develops tooling and manufacturing system products, provides a system to the users, and facilitates initial operations. And 2, operations and support system operations and maintenance, and develops and supports in-service updates. Then we talked about evolutionary characteristics of the development process. Most new systems evolve from their predecessor systems, their functional architecture, and even some component may be reusable. A new system progressively materializes during its development. System descriptions and design evolve from concepts to reality. Documents, diagrams, and models and products all change correspondingly. Moreover, key participants in system development change during development. However, system engineering plays a key role throughout all phases. Then we talked about the system engineering method. The system engineering method involves 4 basic steps: requirements analysis, identifying what requirements are needed; functional definition, translates physical requirements into functions; physical definition, synthesizing alternative physical implementations; and design validation, models the system environment and validates that. These 4 steps are applied repeatedly in each phase during development. Application of the system engineering method evolves over the life cycle. As the system progressively materializes, the focus shifts from system level during the needs analysis down to component and part level during the engineering design. And then finally, we talked about testing throughout the system development. Test is a process to identify unknowns, design defects, and what it verifies, and in that it verifies resolutions of known unknowns and uncovers unknown unknowns and their causes. Late resolution of unknowns may be extremely costly. Therefore, test planning and analysis is a prime system engineering responsibility. All right, thank you very much. That finishes up this chapter.